Dear students, welcome to my YouTube channel PCM Academy. We are in a lecture series of quantum mechanics, and the lectures is basically based on the exam, something like IIT JAM, JEST, NET, GATE, these kinds of exams. Okay, so we are actually discussing about the mathematical tools of quantum mechanics, that is basically the properties of Hilbert space. We have discussed a lot of things about Hilbert space, inner product, orthogonality, orthonormality condition, etc. etc. So if you are new in this channel, then go to the playlist and see all the videos. Okay, and not only quantum mechanics, the mathematical syllabus of mathematical physics is already completed. Mechanics, classical mechanics, as well as electromagnetic theory are in continuing. There are a lot of lectures they are preparing. So I will cover whole syllabus of IIT JAM. Then we will go to the next, that is GATE, NET also. The basic foundation is made in such a way that we can go advanced up to advanced level also. So, but the basic goal of us first to cover the syllabus of IIT JAM. Okay. So, in continuing our discussion of mathematical tools, today I will discuss about eigenvalues and eigenvector. Okay. Eigenvalues and eigenvector. This is also an important topic. Eigenvector. Let us suppose that the state vector phi. Let us suppose that the state vector phi ket. Okay, phi ket, and an operator corresponding to this, which will operate on this phi, will be a cap. Now, if the application of a cap on phi, that is a cap phi, give you lambda phi, then this equation is called eigenvalue equation. Where lambda is the eigenvalue and phi is the eigenvector, you can say, or the eigenfunction, something like that. So this is nothing but the eigenvalue equation. And here this phi is the eigenvector, and this lambda is eigenvalue. So this is a very important thing that you need to know. Now, one thing you should remember, that if this a cap is Hermitian, suppose this a cap is Hermitian, that means a dagger is equal to a. That means a cap is Hermitian. Now, if this is Hermitian, then one thing you should keep in mind in that case, that the eigenvalues corresponding to this operator must be real number. So in that case, eigenvalues will be real, values must be real, this can be proved, but as our goal is this kinds of competitive exams, so no need proof is not very important. You have to just remember this result, and then you have to apply these results in various problems. Okay, so must be real. And one more thing, the eigenvectors corresponding to the eigenvalues will be orthogonal. So eigenvectors will also be orthogonal to each other. Will be orthogonal also. Orthogonal. And if it is q Hermitian or anti-Hermitian, you can say, that is a dagger is equal to minus a cap. I have discussed about Hermitian operator, adjoint operator in the last class. So you can go to the playlist, and obviously if you are new in this channel, then subscribe my channel and hit the bell icon also. Okay, so a dagger is equal to minus a, that means anti-Hermitian, or you can say skew Hermitian. and in that case your eigenvalues will be purely imaginary or zero. Eigenvalues will be purely imaginary or zero. Or zero. Either purely imaginary or will be zero. Now, one more thing we want to understand about this a cap. Sometimes what will happen, this operator will be in the form of matrix form. In that case, we can write phi k vector in terms of column matrix. We have discussed a lot of things about Dirac notation. What is k vector? What is bra vector? But now this k vector and bra vector we will represent by column matrix. Okay, so we know we discussed earlier that this phi k, that is the k vector, is actually state vector, which is known as k vector, and if this is just simply phi, then obviously this bra vector is a complex conjugate of this, something like phi star. So if you want to represent this k vector phi in matrix form, then phi can be write in this way, something like a1 b1 c1. So your bra vector should be written a1 star b1 star c1 star, and this will obviously be a row vector. So this is how we can write, and the operator a can be written in terms of matrix, that is square matrix, something like this: a1 a2 a3 b1 b2 b3 c1 c2 c3. So in this way we can represent this eigenvector and the corresponding operator. Okay, so now let us take an example so that you can understand. Before that, we should know about the secular equation that you have already studied in your matrix courses also. So same thing will be happen over here also. Suppose we have written earlier that we have a wave function or the state vector phi, and the application of a cap on this will give you lambda phi. Now if you modify this equation, and instead of a cap, let me write simply a. Okay, so it will be just a minus lambda i phi equal to 0. That means a minus lambda I equal to 0. So this determinant give you the eigenvalues, and this is known as secular equation. And this equation give you the eigenvalues, and by using this equation corresponding to eigenvalues, we will find out the eigenvector also. Okay, so corresponding to each and every eigenvalue there will be eigenvector. Okay, but if eigenvalues are repeated, suppose you will get repeated eigenvalue, if you get, then it is called degenerate state, or degenerate eigenvalue, you can say degenerate. But if non-repeated eigenvalue you will get, for non-repeated eigenvalue, so it will call non-degenerate. Okay, now let us discuss on problems so that you can understand the whole thing, how we can find out eigenvalue and the corresponding eigenvector, and where and how these eigenvectors will be orthogonal to each other. Okay, so let us take an Hermitian operator, that means Hermitian matrix obviously. So let us suppose that let's take an example in the form of question. Okay, suppose a, that is the operator, is 1 0 0 0 0 1 0 1 0. Suppose this is your operator and you have to find out the eigenvalues, find the eigenvalues and the corresponding eigenvector. And corresponding eigenvector, eigenvectors also, eigenvectors also. Okay, so first what you have to do, if we just write the circular equation of this, okay, circular equation of this, so what we have, a minus lambda I equal to 0, so that will be 1 minus lambda 0 0 0 minus lambda 1 0 1 minus lambda equal to 0. So now if you solve this determinant, you will go to 1 minus lambda, okay, into lambda square minus 1 equal to 0. That means we have 1 minus lambda into lambda plus 1 into lambda minus 1 equal to 0. That means we have lambda is equal to minus 1 comma 1 comma 1. You can say these two are repeated eigenvalue, that means degenerate, and one is minus 1. So we have to find out phi 1, phi 2 and phi 3 corresponding to this 3 eigenvalue. Suppose, let us suppose that lambda 1 is equal to minus 1, so we have to find out the corresponding phi 1, that is the eigenvector. Similarly, if we take lambda 2 is equal to 1, we have correspondingly phi 3, and if we have lambda 3 is equal to 1, phi 2 and phi 3. So we will find out this phi 1, phi 2 and phi 3, that are the eigenvectors corresponding to this eigenvalue. Now what our actual equation was, that was just a phi is equal to lambda phi. Okay, so now if you write this for lambda 1, suppose let us solve for phi 1, so it will be lambda 1, it will be phi 1. So what is a cap here? Just you know that 1 0 0 0 0 1 0 1 0. So this is our a cap, and let us phi can be represented, I have told earlier, by a column matrix. Suppose this is just a1 b1 c1, and lambda 1 is minus 1, and this is also a1 c1. Now by using the matrix multiplication, simple, if you multiply this, what you will get? You will get just a1, okay, and then you will get c1, and then you will get b1. So it will be just your a1, okay, c1 and b1, and here also you have a1 b1, so it will be a1 c1 b1, okay, if you multiply with this matrix multiplication, okay, because this is your 3 cross 3, and this is your 3 row and 3 column, and this is, and here you can see we have 3 row and 1 column, so you will get obviously 3 by 1, 3 by 1, and that is nothing but minus a1 minus b1 and minus c1. Now if you compare both sides, then what you will get? You will get just a1 is equal to minus a1, you will get c1 is equal to minus b1, and you will get b1 is equal to minus c1. So a1 minus is equal to minus a1, which means 2a1 equal to 0. So you can write a1 is equal to 0. So you can choose phi. If a1 is equal to 0, so this is 0, and you can see your b1 is minus c1, and here also b1 is minus c1. That means b1 and c1 are same. So you can write this as b1 and b1. So this is your phi. Now, if you normalize this wave function, suppose let us write in this way. So that phi with phi will be 1. This is the normalized condition we have discussed earlier. So if you have phi, that is bra vector, that means it will be 0, b1 and b1. b1 star, b2 star, b1 star, you can say as this is something like this, and this phi will be 0, b1 and b1, and that will be equal to 1. So now if you multiply, you will get b1 b1 star and b1 plus b1 b1 star. That means b1 square plus b1 square, that is equal to 1. So we have 2b1 square equal to 1. So b1 square equal to half. So b1 is equal to 1 by root 2. So finally you will get phi. That means phi 1 actually this. Actually phi 1. So finally you will get phi 1. And this phi 1 with phi 1, if you so what will be our phi 1? That is nothing but we have 0, b1, b1. Now if you take common b1, then it will be 0, 1, 1. And this b1 is 1 by root 2. So it will be 1 by root 2, 0, 1, 1. So this is our phi 1 corresponding to lambda 1. Now how you can get phi 2 and phi 3? So in that case, you have to use another also, that is, for lambda 1 is equal to 1 and lambda 2 is equal to 1 and lambda 3 is equal to 1. So if you use this and if you follow the same procedure, then you will get obviously lambda phi 2 and phi 3 also. Phi 2 and phi 3 also. So I am giving you this as your home task. So you can find out the phi 1, that is the eigenvector corresponding to the eigenvalue. So be careful and find out in this way. But you can see, if you solve this, you will see that this phi 2 and phi 3 you will get this phi 2 and phi 3 in the form of something like this kinds. That is phi 2 is equal to, suppose, a2, b2 and b2, and you will get phi 3 as a3, b3 and b3. Okay, you will get in this form, and you will get a lot of phi 2 and phi 3 corresponding to the value of a2, b2, b2 and a3, b3, b3. But which value you should take of a1, a2, b2 and b3 and a3 such that they are orthogonal to each other? That means obviously you have to find out phi 2 and phi 3 in such a way that phi 2 with phi 3 equal to 0, phi 1 with phi 3 equal to 0, and phi 3 with phi 2 phi 3, phi 1 phi 3, and phi 1 phi 2 and phi 1 phi 2. This all will be 0. So this condition will hold. You have to find out phi 2 and phi 3 such a way. Okay. So if you follow the same procedure that I have said earlier, if you follow this procedure, so find out, put just here 1. Okay. So if you put here 1, then obviously you will get, instead of 0, you will get just here a value, that is a2, and this 2 will be equal, that is b2, b2, and for phi 3 that will be same, so it will be a3, b3, b3. I have just given here the different notation, but this will be same. But you can't choose a2, b2 and a3, b3 in such a way that this phi 2 and phi 3 are same. You can't choose. You have to choose a2 b2 and a3 b3 in such a way that this orthogonal condition will be satisfied. So this is the real challenge here. Okay, so this is how we will use, and I will solve later on this kinds of thing also. So please do this exercise, then you can understand what I want to say. Okay, so for today, thank you.